Good morning everyone and welcome to a new video about the Gemini x02 amplifier. First of all, I want to thank all the English and Italian viewers that left some positive comments and feedback on the videos. Actually, I started making this series of videos for some of my friends, but it got more popular than expected and it made me really happy, so thanks everyone. So I never talked about my personal background. I'm just a college student and my hobby is indeed repairing and restoring amplifiers for friends, family and other people that ask me. But lately I had the idea of making some videos about what I do, thinking it could be interesting because sometimes I find really interesting things in the amplifiers or machines I open up and in the circuits I analyze. So yes, from now on I will take things a bit more seriously. I will go back and correct some mistakes I made in the previous videos, adding some useful information maybe and doing a well-requested circuit analysis since a lot of people and friends asked me to do that. Talking about that, I need to thank the colleagues of the university for lending me a very useful manual for understanding the different kinds of amplifiers and their characteristics. The manual is Designing Power Amplifiers, written by Bob Cordell. It has more than 600 pages and it's packed with useful information about the topic and a very interesting read. So if you're interested about amplifiers and wanting to know more about them, I suggest you read that book. In this video, I want to talk about the circuit of the amplifier itself. I got some negative comments about this particular brand of amplifiers, but I can assure that apart from the power section, the rest of the amplifier has really good specs and the circuit is quite well implemented, so like we will see in the rest of the video. So looking at the schematic, the first thing we notice on the left is the input signal section. The same 4558 operational amplifier, because it contains two operational amplifiers inside, is used as both input stage, considering the amplifier accepts both balanced and unbalanced audio signal, and the second one is used as driver of the amplification stage. On the circuit board we can also see that some of the resistors are in the form of this long vertical mount resistor array, which reduces trace length and the overall area of components that we'll take. It's a quite good choice. Here we have the potentiometers for signal adjustments, and down here a switch that selects the various working modes of the amplifier. It can be dual stereo, parallel and bridge mode. In stereo mode, the two channels are driven separately from the two different audio inputs, like you would expect in any other kind of amplifier. In parallel mode instead, both channels will reproduce the sound presented at the channel 1 of the amplifier, of the input connector. In bridge mode instead, the channel 1 will reproduce the audio presented on the channel 1 input, but the channel 2 will reproduce the same audio but inverted on the y-axis. This allows for a bridge connection, which I will explain more now. The speaker can be connected between the positive terminal of channel 1 and the positive terminal of channel 2, ensuring that the peak-to-peak voltage is doubled than a normal connection, not a bridge connection. This means that according to the Ohm's law, this is a consequence of the Ohm's law, P equals V squared divided by R. So if we double V, the output power is 4 times. So in other words, how do we calculate the output power of an amplifier? Because I had a few people asking me that in the past and I think it's a quite interesting thing to learn. We only need two parameters. We need the power section voltage and the speaker impedance. In this case of the Gemini x02, the voltage of the power supply rail is minus 60 volts, 0 and 60 volts. The two rails are symmetrical. The formula for calculating the max power output is, for example, with an 8 ohm speaker, is P equals V squared divided by R. But we need to keep in mind that the signal at the output of an amplifier is not DC, it's AC. So we need to calculate the RMS actual voltage. So we don't use V in the formula, we use V divided by the square root of 2. In this case, doing the calculation, we obtain that the max power output is 225 watts, but yes, we understand that this is just a theoretical number It doesn't take into account the power dissipation of the transistors and the resistance of the cables and the power losses. We can assume though that the value of 140 watts provided in the datasheet on the amplifier is indeed correct. But this is in stereo mode. What happens in bridge mode? Well, in bridge mode, V is not 60 anymore. It's 120 because the peak-to-peak voltage now is from plus 60 to minus 60. So 60 plus 60 is 120. So if we take that new number and divide it by the square root of 2 and then put it at the power of 2 and divide it by R, we get that there is an increase of 4 times the previous power. So in this case, if we assume the previous power to be 140 watts, 4 times that means 560 watts. But again, removing losses and power dissipation, we can still assume that the 400 watts provided in the specs of the amplifier are correct. So that's very good. The only limiting factor here is the size of the heatsink, the amount of the transistors, because you can't dissipate more than 120 watts on these transistors. So yes, you need to take that into account, but 400 watts seem quite fine and realistic. So let's go back to the actual circuit, now that we know that the specs are correct. We can see that in this section here of the circuit, the second operational amplifier is used to drive a transistor, and then this transistor drives the rest of the amplifier section. The feedback that comes from the amplifier and the speakers goes back to the non-inverting input of the op-amp, and this is used to ensure a correct output all the time, no matter the load of the amplifier. We can see that there are two transistor networks, the one made by Q5 and Q6, and the other made by Q10 and Q11. And there are also two resistors here, R25 and R39. These are used for the correct polarization of the output stage and to create the bias current for driving the amplifier in class AB. So this amplifier doesn't need manual adjustment of the bias current. It's completely automatical and it's given by these two transistor networks and the two resistors. So this removes entirely user errors and that's quite good. Also, the LED LD1 that I talked about it in a previous video is part of the biasing circuit, but it's also used as an indicator to show that the channel is working properly. In the third part, we can see that the two transistors Q27 and Q13 are used for overload and short circuit protection. In fact, they detect the voltage across the emitter resistors R51 and R42, and they ground the bases of the transistors Q26 and Q19 if the voltage across the resistor is too high, and this prevents the amplifier to break down and explode basically. Finally, the transistor Q26 and Q19 are used to drive the powered transistors of the output stage in a Darlington configuration for more power. And then we have the output transistors Q23, Q24, Q18 and Q20, and they are good quality Toshiba transistors and they are mounted on the back of the heatsink you saw in the previous videos. So yes, we can see that overall the amplification circuit is quite good and the choice of components and the design is not bad. So it's not like some people say it even has its own integrated protection circuit, so it's quite good. Also, apart from the amplifier section, this amplifier has temperature protection, an anti-bump system and other clipping protection to ensure that there will be no problems whatsoever. Let's see here the protection circuit. So there is a relay here that closes the circuit to the speakers, and this relay is toggled only when the capacitor C43 is fully charged, and this takes a few seconds after we turn on the amplifier, and this removes the bump sound when we turn on and off the amplifier. There is also a PTC sensor. It's RT1, and it's a positive temperature coefficient resistor, and it's attached to the heatsink. This special kind of resistor changes the internal resistance based on the temperature of the heatsink. If it gets too hot, I measured 90 degrees Celsius, the resistor stops conducting electricity and it cuts the relay from the power section, disconnecting the speakers and ensuring that the amplifier will have some time to cool down. And then we have the fan circuit. We talked about it in the first video I made. The fan is used to feed the other part of the circuit, and this also means that if the fan stops working for some reason or it gets damaged, this will cut off power to the relay and the amplifier will go in protection mode, and this is very good. So there are a lot of safety features in this amplifier despite it's quite cheap. Also, there is no need to worry about interferences from the fan because they used here a chunky capacitor to reduce the voltage spikes and interferences coming from the fan, and they added a few smaller capacitors near the operational amplifiers to ensure that the power that goes to the op-amps is nice and clean. Let's sum up everything. Like, there are positive and negative aspects of this amplifier. The power section is poor and needs some improvements. We've seen that the input capacitors are not big enough, so I replaced them with some bigger ones. Also, let's say that the preamp and the amp section are good and they work decently enough to produce a clean and accurate sound, so I wouldn't worry about that. The only main concern is the heatsink because it's undersized for the specs of the amp, and there are no heatsink on the voltage regulators made by x02 and Q3. So I had to add some heatsink there to ensure that transistors don't go in thermal runaway and they don't melt down. I've been browsing the internet trying to find more information about broken units, and overall the majority of broken units had the two transistors Q32 and Q3 broken, probably because of the excessive heat, and also the potentiometers rusted and not working anymore, so they had to be replaced. I fixed all of these problems. I used heatsink on the transistors, I replaced the potentiometers, I added a silent fan with the thermostats that only triggers about a certain threshold of temperature, so overall we made a quite good amplifier. So yes, overall I would rate this amplifier 3 out of 5, I guess. It could be better in some important aspects like power dissipation and power supply, but overall the amplification section is quite good, so I'm quite impressed by that. Well, we reached the conclusion of this video. I hope you found it interesting. In the next video, I will mount the amplifier back together, add the view meters, and test the amplifier with an oscilloscope and provide more details about the accuracy of the output signal. So stay tuned and see you on the next video.